Phil from Blueprint MCAT. How you doing today?
I'm doing fantastic. I'm excited.
I'm excited too. We're going to jump into, so a couple months ago, many months ago, we went through all of full length 10 from Next Step Test Prep. Now we're going to go through all of full length 1, which is a test that any student can go and sign up and get for free. By signing up for the diagnostic, they also get full length 1. I don't think students really know that or understand that. But I'm excited to take the next probably couple months with the MCAT podcast and go through full length 1. And we're going to record video this time as well so that students can really see how we work through the passage, how we go through the questions. And this will be, I think, an amazing resource for students as they're reviewing full length 1 that they get from Blueprint MCAT.
Yeah, it's super exciting. I think the video stuff will come along really well and kind of make it a lot easier, especially when we're doing like data interpretation. There's a lot of like stuff you need to kind of like look at in order to answer the question.
Yeah. So if you want to work through this with us, then you can go sign up for the diagnostic and full length exam at blueprintprep.com/MCAT. Or you can listen to this or go through everything first and then listen to this or watch this on the back end as you're reviewing. So many ways to skin the cat here. Let's go ahead and jump in. So we're going to start at question 1, passage 1, Chem Phys, as if we're going to sit down and take the test.
Right. So, it's 8 a.m. test day. I've had my oatmeal. I went to the test center. I'm ready to get going on this.
Yeah. And so for the students listening to this, we'll still read the passage, or Phil will be kind enough to read the passage, and we'll make it as audio friendly as possible. But then it'll be nice to have the YouTube videos as well to go back and look at the graphs that may be referenced.
Yep.
All right. So let's go ahead. Passage 1.
All right, let's jump in. So start off here, passage has got 5 questions. Just kind of glancing at the passage, there's a couple of figures. Looks like some like graphs that are a little bit complex. I think it's sometimes nice to kind of just get a feel for a passage before I jump in. Passage starts off a hypersaline body of water. So I'm thinking salt, water, this is going to be a chemistry passage for the most part, although they might throw a couple of physics things in there. So let's go ahead and kind of like jump in here and actually go into the deep end, if you will.
Okay.
So a hypersaline body of water contains high concentrations of sodium chloride, salt, and other water-soluble ionic compounds such as calcium sulfate, gypsum. So as I'm reading this, the calcium sulfate, and they told me that's gypsum, I'm thinking okay, maybe there's something with a chemical structure that they might be asking about coming down the line. So the salt levels exceed those found in ocean water, which contains 3.5% sodium chloride by mass, and are often associated with flora and fauna that are specifically adapted to these extreme conditions. There's considerable interest in species that can survive under such conditions because they may represent conditions for life on other worlds. The best known hypersaline lakes are located in the hydrologically isolated environments in which water inflow is in equilibrium with evaporation. Examples include the Dead Sea in the Middle East and the Great Salt Lake in Utah. Salt concentrations in the Dead Sea are greatest in the southern section and approach saturation. So it's talking about saturation levels. So I'm thinking KQs, KSPs, expecting maybe to see a question about this. Also, the MCAT is kind of doing a classic thing here. Examples include the Dead Sea, DS, and the Great Salt Lake, GSL. And then for the rest of the passage, they're going to be saying DS and GSL. Why? Well, they could write out Great Salt Lake, but this is just a way for them to ramp up the difficulty a little bit by having some acronyms that we kind of have come back to.
Yeah.
So I look at this salt concentration in the DS, it's Dead Sea. And I need to make sure that I understand this as I'm going through.
Okay.
So salt concentrations in the GSL range, Great Salt Lake range, from levels similar to ocean water up to saturation. Swimming in salty water is a significantly different experience than swimming in fresh water. I'm going to pause, right? As I'm going through this, everything to me so far has kind of screamed chemistry, solubility, saturation stuff. The moment I see this with the swimming, I'm like, oh, buoyancy, right? And so there might be some more physics questions coming down the line. So the average human body has a slightly greater density, 1.01 kilograms per liter, than fresh water, and people must usually swim to stay afloat in a body of fresh water, like Lake Michigan. However, adding salt to water increases the density of the liquid, resulting in an increase in the buoyant force. Buoyancy. The salt also affects other properties, including colligative properties such as reductions of vapor pressure, figure 1b, melting point, and solubility of gases. So as I read that, I'm thinking colligative properties are also coming down the line. So I think it's really important, like as you're reading a passage, to be like to realize what stuff you need to pull from it and what kind of questions you would expect to see, because that makes it easier for you to kind of anticipate what the exam writers are trying to do. And so there's stuff that I've kind of seen through this is like, okay, saturation stuff. We have things with buoyancy, things with vapor pressure and melting point, those kind of colligative properties. There's also a fair amount of numbers, right? The like 1.01 kilograms per liter is a human body density, or the 3.5% sodium chloride by mass found in ocean water. So I think it's important to kind of like be thinking about those as you're dealing with the passage. So after that, we have this figure here, which is showing the solubility in relation to temperature for a bunch of different salts, right? We have sodium nitrate, calcium chloride, lead nitrate, potassium nitrate, a lot of nitrates going on here, potassium dichromate. There's kind of like a big mix of them. What sort of thing, looking at this, kind of like jumps out to you, Ryan, like if you're kind of like looking at what's going on here?
I have no idea.
Right. Seems like a lot of just like lines crossing over. It looks like,
there's a few that are outside of kind of the realm of where kind of everywhere else is going, but yeah, it's all crazy.
I would say for the most part, all of these tend to be like really greatly increasing as temperature goes up. The water becomes more soluble for these. Like you said, I think there might be a couple of exceptions looking at this. Which ones kind of like jump out at you?
So was that calcium chloride? Is that CaCl2? Chloride, whatever that is.
Yeah.
So that one, just exponential growth almost immediately.
Right.
Shoots off the top of the chart. And then this Ce2SO4-3.
The cesium sulfate.
Yeah, cesium sulfate. That one looks to be the only one that goes down in solubility as temperature goes up.
Right. Yeah. And so that one's actually like all the other ones seem to be increasing. That one seems to be decreasing. So it's kind of an odd one out, which like makes the hair on the back of my neck stand up. It's like maybe there'll be a question about that. Another thing to note that's kind of interesting is sodium chloride, which is probably the most well-known salt, is just like it's close to flat. It is increasing, but it is kind of flat. So that means that water at like 80 degrees is not all that, doesn't have that much higher of a saturation point than water at like 20 degrees. Versus for these other things, like, you could triple or quadruple the amount of salt in the water in those temperature ranges. So we also have another figure here, which is a graph of like pressure and temperature comparing like solid, liquid, and gas. People who have studied for the MCAT looking at this, like this is not like weird. Like you've seen probably this figure before. And so there's some things on this graph that are not being shown, words you're probably familiar with, like triple point and the critical point, which is like the solid liquid graph keeps going as like a straight line forever. But the liquid to vapor or the liquid to gas usually ends in kind of a point, and we call it the critical point. And like anything after that is kind of a liquid, is kind of a gas. We're not really sure. We call it a fluid at that point because the liquid and gas are both fluids. Okay. So definitely some things kind of going on with this, but we're not quite done with the passage.
Okay.
So hypersaline bodies of water tend to be fairly sterile, containing only highly adapted forms of life. Brine shrimps are the most notable aquatic life form in the GSL, Great Salt Lake again. The shrimp feed on algae by mastication using mandibles to create a bolus, which after injection into the mouth travels down the equivalent of the esophagus to the stomach. What do you think about that sentence there, Ryan?
I'm thinking I was just reading about water and solubility, and now I'm reading about physiology.
Right, yeah, a little bit of crossover into physiology. I also think that this is like the most wordy way ever to say the shrimp eat the algae, right? Like they masticate using mandibles to create a bolus, right? Basically, they chew it up and they swallow a chunk of it. Yep. And then it goes to the stomach. The shrimp ingest a lot of salt during this process, which is excreted through the branchia. This is not something I don't think humans have. I don't remember that in anatomy and physiology.
Yeah, no.
In addition, anaerobic halophiles can be found, namely fermentive, sulfate-reducing, homoacetogenic, phototrophic, and methanogenic bacteria.
Yeah.
So a lot of fun words there that you get a lot of points in Scrabble with.
Yeah, I think the test writer just has fun with, like, let me just throw in a bunch of really big words and make everyone scared.
Yeah, and that's like it's not just to make people scared. Like this is something that like it's just ways for them to ratchet up the difficulty because MCAT students are smart and it is very hard to separate them sometimes. And so they'll just like take this and like ratchet up the difficulty by using language that's a little bit more complex or a little bit less comfortable for students. Like instead of light in the entire passage, they'll say radiation, which is just light.
Yeah.
Yeah.
Okay.
So we have question number 1. What's the approximate solubility of sodium chloride in ocean water if the density of ocean water is 1.028 kilograms per liter?
So the first thing that I would do, the answer choices here, A, 0.026, is that molar? Is that how you say that? Mm-hmm. Capital M. It goes by so fast. B is 0.62 molar, C is 0.96 molar, and D is 9.6 molar. So the extremes I always like to throw out. I'm like, well, that's really small and really big, but I don't know if that's the right thing here. Obviously, 9.6 is on the other end of 1, and everyone else is below 1, so that stands out. The molarity, I'm going to go back to the passage and go, okay, where did they talk about molarity? And I don't think it was talked about at all. So then I'm like, did I already, am I going to miss the first question? Because I don't know what I'm supposed to have. So
they're asking specifically about ocean water, right? So in my mind, I'm going to go back and see if there's something I can find with like ocean water in here. And I think there is actually something in this like first paragraph. I think it's the second sentence.
Yeah, it contains 3.5% sodium chloride by mass. So are we supposed to just take the density of ocean water is 1.028 and multiply that by 3.5%?
Yeah, and then you'll find how many grams of sodium chloride you'll have. Now, that's still not going to get you to molarity necessarily.
Yeah. Okay.
And so how can we go from that, like the grams of sodium chloride to molarity or to moles of sodium chloride?
Avogadro's equation?
Yeah, well, you're close.
Avocado's equation?
The avocado equation, yeah. So you definitely, this is where we start to utilize, like we're on question 1. We're already utilizing those like little extra things that the MCAT gives us access to, like the periodic table.
Oh, periodic table. Okay.
We can figure out we can pull up the periodic table. You can kind of look at chloride is 35 grams, sodium is 23 grams. I'm going to do some rounding because I'm on the MCAT, right? If the answer is 27 and I'm like, it's less than 30, that's good enough for the MCAT. So we can do some rounding here. Okay. So sodium's 23 grams, chloride's 35. You add those together, and it's about 60. Okay. Right? Somewhere around there. I would say about 60 grams per mole. Okay. And so we can take this, take the density of water, which is 1.28 kilograms per liter, multiply that by 3.5%. In order to find the actual grams of sodium chloride that we have. And then convert that to moles, and then we have moles per liter. I actually think that there is perhaps an easier way to answer this question. Okay. For students who, there's like a back door. I like talking about back doors to question where it's like, there's like the hard way and then there's the easier way. So most students are pretty comfortable with the idea that water is 1 kilogram per liter, just like fresh water with nothing else in it. Yep. And so if we look at this, I'm going to say there's about 28 grams in this because the water is 1.2028 kilograms per liter. So water counts for one of that. The 0.028 is the sodium chloride. Now that's not actually like a pure number. It's actually going to be like 0.29 or 0.27 or something like this. But this, once again, we're on the MCAT. We can do some ballpark math. And so if sodium chloride is about 60 grams and I have like 28 grams of it, then how many moles am I going to have in that case?
I don't know.
So if I have 28 grams and it's about 60 grams in a mole, it should be like about half a mole.
I was going to say half. Okay.
Yeah, it's about half.
Okay.
Right? And so I'm going to go with the answer that says about half.
Yeah.
So
0.62.
B. Yeah, 0.62. And so that's the short way to do it. Kind of like saving some time calculating, just be like, it's about 28, it's 60 grams per mole, so it's about half of that. So it's about half a mole, and that makes B the correct answer.
Okay, so I'm going to pull up the periodic table again, and as I pull it up here, I'm looking at sodium 23, chloride 35.5. So again, about 60, right?
Right.
And so if I just look at one of these, so if I just look at sodium, that's 20, there would be 23 grams per mole. That's how I could interpret that. Okay.
Yeah, there'd be 23 grams of sodium to make 1 mole of sodium.
Okay.
Yeah,
awesome.
Absolutely.
So that makes it easy.
Yeah.
Okay.
And so I think this is also, just kind of like taking a second. I know we're trying to get through questions, but this, like in undergrad, you're kind of punished for rounding.
Mm-hmm.
And like if you're on a physics exam, the answer is 27, you say it's like, it's less than 30. Like you failed, right? Like you did not get the point.
Yeah.
But on the MCAT, all of a sudden that becomes not just like okay, but useful and perhaps crucial on some questions to like learn. Because I really don't want to take 1.028 times 0.035, right? Like I don't have a calculator. I mean, I can do that on scratch paper, but if I don't have to, I'm really going to try to avoid that.
Yep. Makes sense. Okay. Awesome. So click next here, go to question 2.
Yeah.
So I'll read this one. If a person drank a large quantity of hypersaline ocean water, the person could die because absorption of salt into the blood will cause it to become A, hypotonic compared with the cytosol of the body's cells, causing osmosis of water into the cells. B, hypertonic compared with the cytosol of the body's cells, causing osmosis of water into the cells. C, hypotonic compared with the cytosol of the body's cells, causing osmosis of water out of the cells. Or D, hypertonic compared with the cytosol of the body cells, causing osmosis of water out of the cells. And so I'm looking at this and rephrasing, okay, if I drink a lot of ocean water, what's going to happen? And so A and B are water into the cells, C and D are water out of the cells. So if I drink a lot of hypersaline ocean water, I'm going to get a lot of salt in my blood, right? Just generically thinking. And so I would say it is hypertonic compared with the body cells. So A and C are out. And because it's hypertonic, the water in the cells is going to, I think, want to go out of the cells to try to balance that out. And so I would end up with D, hypertonic compared with the cytosol of the body cells, causing osmosis of water out of the cells.
Right, exactly. So water is going to move out of the cells into the blood. This is also why, like drinking salt water, probably not a good idea, but like eating salty foods, also maybe not a good idea, but less bad of an idea. Eating salty foods are going to do kind of the same thing. It's going to pull water out of your cells and into your blood, which is going to cause your blood pressure to go up. So that's why people who have high blood pressure should probably be avoiding salty foods. But yeah, exactly.
Cool. All right. Next question. Go ahead.
Right.
You can take this one.
All right. Based on figure 1, adding salt to water causes the boiling point of water to increase, requiring greater kinetic energy of the liquid to produce a vapor pressure equal to the external pressure. Increase, or B, increase, requiring a greater average kinetic energy of the liquid to produce a vapor pressure that is greater than the external pressure. C, decrease, requiring a lower average kinetic energy of the liquid to produce a vapor pressure equal to the external pressure. And D, decrease, requiring a lower average kinetic energy of the liquid to produce a vapor pressure that is less than the external pressure. So this is another one kind of like that last one where there's kind of like increase, decrease, decrease, right? Like you can kind of like, if you figure out one thing, you can kind of like get to a 50-50 at that point.
Yeah.
And so most students are going to be pretty comfortable with like adding salt to water. Like what does that do to a boiling point? Even just from like outside knowledge without like looking at figure 1.
Yeah. You add salt to increase the boiling point. So the water is hotter. It boils the noodles faster.
Right. So so it boils hotter. Exactly.
Hotter,
Turns out you have to add a ton of salt to actually make a difference, to like cut your time from 3 minutes to 2.5 minutes. It's got to be like basically just a pile of salt. But yeah, so we're going to expect the boiling point to increase.
Okay.
Right. And so the answer has got to be A or B at that point. And that's great because we've done no work. I just know what my mom told me whenever I was cooking pasta.
Yep.
And so at this point, we just need to figure out, like, is it because it requires greater average kinetic energy to produce a vapor pressure equal to the external pressure, or a greater average kinetic energy to produce a vapor pressure that is greater than the external pressure? So these two questions are very similar. It's just asking us, like, okay, well, when does water boil? Does it boil when vapor pressure equals the external pressure, or when vapor pressure is greater than the external pressure? This is another kind of like pseudo discrete question that requires you to kind of have some outside knowledge that's a little bit specialized.
Yeah. Equal to or greater than. I don't know. Something tells me equal to.
Yeah, so it is equal to. So the water molecules kind of like bouncing around inside the water. Mm-hmm. If they're going the same, they're kind of like hitting the surface of the water with the same pressure as the force of the air pressing down, then it's like equal pressure or equal forces, and it's not going to like slow down. So when it hits this, it's just going to keep going because the net force is going to be like zero. Yeah. And so you want the average kinetic energy of the liquid to be equal, but the vapor pressure has to be basically equal to the external pressure.
Okay. What happens if it's greater than the external pressure? That sounds like a bomb.
Yeah, it basically would be kind of this like superheated fluid that's going to basically kind of explode into steam.
Yeah, we don't want that.
Yeah, a little bit scary there.
Not for my kitchen. No, thank you.
Yeah.
Okay.
Yeah. So my pasta.
We end up with A, increases the boiling point, requiring a greater average kinetic energy of the liquid to produce a vapor pressure equal to the external pressure.
Okay. Right, exactly.
All right, question 4. Water is a rare substance in that the solid is less dense than the liquid at the freezing point, resulting in a solid form that floats on top of the liquid. Ice cubes. Which of the following best explains this phenomenon? A, the bent structure of the water molecule results in a molecular dipole that maximizes the close molecular packing structure in the solid state. B, the bent structure of the water molecule and ratio of covalently bonded hydrogens to lone pairs of electrons on the oxygen atom maximizes the hydrogen bonding that occurs in the solid phase, producing a hexagonal structure with large empty spaces. C, the degree of ionization in the solid state is less than in the liquid phase. D, the London dispersion forces of water significantly decrease in the solid phase as compared with the liquid phase. Wow. So we could go with my handy dandy, like the answer that is the most crazy is probably the right one. Because the rest of it, like London dispersion forces, I don't remember any of this. I think I remember something about the bent structure. So I'm with A and B being something. And just me thinking logically about what makes things float. Well, if there's lots of air in there, then things float. And if there's lots of empty spaces, there must be lots of air. So I would go with B, just using some common knowledge and some potential random knowledge about bent structures being important. Yeah,
absolutely. That's actually the correct answer. And the kind of thought process you have through this is like this. There's a lot of stuff in these answer choices that might be true, they might not be, right? Like maybe you know it, maybe you don't know it. Like obviously, the more you know, the better off you are. But this question is asking, what explains why ice floats? And B is just saying like, oh, there's these big empty spaces, so that makes it less dense. And so whether or not A, C, and D are even true, B is the only one that actually explains why something might float. And so B is going to be the best answer there. Yeah. And so you can kind of get away even if you're unsure of what these things mean overall.
Yeah, best explained. So you got to catch that question.
Okay. Yeah, making sure that you're answering the question, because that's a common trap that the MCAT sometimes sets, where students are looking through the answer choices and they're like, I don't know if that's a thing. I'm iffy on that. This is a thing. I know that's true. And then they want to pick it, but it doesn't answer the question.
Yep.
Right. The question is like, what makes ice float? And there's a question that's like, there's there's water in your blood. And like, yeah, that's it. Like that doesn't explain why it floats.
Okay. All right. So we got B for that one.
Yeah.
All right. And go ahead.
So question number 5, what is the chemical formula for gypsum? Ooh, saw this question coming as we were dealing with the passage. So this is a pretty straightforward. It's CaSO3, CaSO4, Ca2SO3, or Ca2SO4. This requires you to know those polyatomic ions, those things that all your teachers have been trying to get you to memorize. At least for me, I feel like I was lectured on these probably 3 or 4 times. Luckily, they finally stuck. So the passage itself says that gypsum is calcium sulfate. And so all of these answers have calcium, so that doesn't help. But only some of them have sulfate. So if you know what sulfate is, do you actually... How comfortable are you with the structure of sulfate compared to sulfite, which is the other one that's going on?
Sulfite, I think, is SO4?
Nope.
Switched them. Darn it. Okay.
Yeah. So here's a quick way to remember this. So there's like phosphate and phosphite and chlorate and chlorite and all of those. The 8 always has more oxygens than the ite does. Okay. And so SO4 is going to be sulfate and SO3 is going to be sulfite. Same with nitrates and nitrites as well.
Here's an easy way to remember that. The 8 ate one of the oxygens.
Right. Yeah, it ate more. It's bigger. Yeah.
Okay.
And the ite, they asked it if it won anymore. It's like, nah, I'm ite.
I'm ite. So sulfate would be SO4, so that gets rid of A and C. And now we have to know, like, which is the question, like, which one is balanced, Ca2 versus Ca?
You're right. Exactly. So the key here is knowing that sulfate is not just SO4, but it's SO4 2-. And so it's got a -2 charge. And calcium, if we look at our periodic table, kind of like pull that up, calcium, because it's in that second column, that means it's most likely to lose 2 electrons. And so calcium kind of wants to be calcium 2+. Okay. So if calcium wants to be 2+ and sulfate is 2-, the actual proper balanced version of this is going to be which one?
B. CaSO4.
Right, exactly. Yeah, CaSO4. Okay. If you have trouble remembering that it's got the sulfate's got the -2 charge, there's that. What's that? There's like a rhyme from, Billy
from
something.
Busta Rhymes?
Billy, yeah, no, not Busta Rhymes. Billy is no more, because what Billy thought was H2O was H2SO4.
I don't know.
He drank something. Yeah, it's a story about like not just drinking random stuff in Chem Lab. Sometimes you need to teach students don't just drink from bottles.
Yeah.
So H2SO4 is going to be sulfuric acid, and it needs the 2 hydrogens because sulfate's got the 2- charge.
All right, so there you have it. Passage 1, full length 1 from Blueprint MCAT. Again, medicalschoolhq.net/blueprint will take you to their new website. Hope you have a great week. We'll be back next week for Passage 2.